Okay. That's my face. Hello. So we are going to build a Game Boy emulator today. My name's Pat. I'm from Oneflare, a startup in Sydney. I'm joined today with Fatima to my left. Say hi.
Hello.
And yeah, we're going to start building a Game Boy emulator. Now, we kind of were working on one in the past, but I realized we didn't actually save any of the videos, and we want to upload these to YouTube, so we're just going to start from scratch. But we're going to kind of do it a bit quick. So to start with, we're going to just get our Xcode project to a point where we can display pixels, because obviously we need to do that. So just jump on Safari or Chrome or whatever and go to libstl.org, and then what we're going to want to do is download the source code here, so this guy here, and it should download fairly quickly. And then let's have a look at what we get. So we get a bunch of stuff in here, right? We get a bunch of like starter projects, but they're not really starter projects. They're just kind of like nothing. So we can't really use them as starter projects. We can't like load this project and then work on it. We have to import it into a existing Xcode project. So let's keep this to one side. Let's open Xcode and we'll go File, New Project, and I'll just drag this down here so I can actually see it. And then we're just going to make a macOS project. Call it whatever you like. Let's call it Game Boy or whatever. And then just store it wherever you like. Let's pop it into this conveniently titled thing called Gameboy Series. Let's pop it in there. Okay. So the first thing I like to do when I create a new project is just to build it and run it and just make sure we get something. There's no reason to think we won't get something, but let's just try it anyways. Hello world, cool. That's great. Did I do a source code project? I did, didn't I? Oh boy. Yeah, alright. So, this isn't part of it. What we need to do is just do that again, but not do a source code project. Give me a second, yeah. Alright. That's totally intentional. Project. Drag this down here. Coca app. Next. Game Boy. It's fine. Next. And that works great for me. You kind of see behind the curtain there a little bit as well. Alright. So let's do the same thing again, build and run, and we'll just make sure that we get the screen. Whenever it's ready. There we go. Alright, cool. Awesome. Very boring, but that's fine. So what we're going to do now is just add all the STL stuff. This is actually pretty easy, so let's go through it together. We've got to grab that directory that we had before. Yeah. And we want to just go into the Xcode directory, into the STL directory, grab this guy here, and we're just going to literally drag it into the project. It's just going to add it there, but it's also going to give us all of the extra things that it comes with. So these things are all going to be in red because we haven't built it yet, but that's okay. Then the second thing we need to do is go back to the STL folder and grab the include directory, and this is going to have like everything. And we drag it into here as well, not at that level. We drag it at this level. We don't want to copy items if needed, and just kind of have it match these settings. Finish. Perfect. And then we need to go to build phases, link binary with libraries, and we want to, you'll get these new ones from the workspace now. We just want to add this one, libstl2.dylib add. All right. So now if we build it, it should run. We won't actually see anything, but it should run, and that's what we want to see to begin with. And then once that's good, we'll get a test screen. So SDL's like, it's like a way to just draw stuff to a screen. I think it stands for Simple Dynamic Layer, and it's kind of what a lot of video game engines use in the background, but you can use it for really anything. We could use, say, Cocos 2D, or we could use SpriteKit or anything like that. But for this, we kind of want something that's really fast and really low level, because we're going to have to do a lot of operations every second. So it just makes sense to use libstl, and it's open source as well, so it's pretty fun. All right, so we've got a window here, everything builds. If we had done any of those steps wrong, it would fail, but that's fine, it didn't. So now what we're going to do is just actually get it to draw something. So in the view controller, we'll just put the view did appear method in there. We'll call it super. Then we're just going to use this sample sample draw display window thing that I wrote ages ago. So I'll write it out with you. We want to import sdl.h. Very good. And then we want to make a new method here. I don't know, display test window. Doesn't really matter what you call it. All right. Cool. So we need a couple of things. We need a reference to the SDL window. We need a reference to a renderer as well. This series isn't really going to go too much into how how SDL works. I'll explain things as we go if I can, but there are a lot of things that are quite complicated, so I will have to kind of breeze over a couple of like SDL related things. But you can find like much more information than I would ever be able to explain on that website anyways, and there's tons of tutorials and stuff online as well. So we want to check if it actually initialized init video. All right. So if it didn't initialize, so the error is like less than 1 or 0. No, sorry, less than 0. So it'd be like -1, -5, whatever. Then we don't do anything. Just log something. Whoops. Whatever. Spell whoops correctly as well. Otherwise, we need to create a window and renderer. Create window and renderer. And here we get a chance to set its width, its height, some window flags, and all that good stuff. So the Game Boy's width, if we look at the Game Boy programming manual, which we'll put a link to in the YouTube video. It's just a couple of documents online that were written ages ago. If we look at that, the resolution is 160 by 144. So we'll make the width 160 and the height 144. Window flags never really used, so we'll just put 0. And now we have to put we have to pass like pointers to the window and the renderer. So we'll do that with the ampersand. There's the window and the renderer. All right. Now we can set a title. Let's do that. Set window title. And we pass in the window. We don't need to dereference it because it doesn't. If you look at what it's asking for, it's not asking for a dereferenced version of it. It's only asking for like a single star. So you can just pass it in. But the other one, I'll just do that again. Create is asking for like it's got the 2 stars there, so we need to pass with the ampersand. Alright, and then the title. It needs to be can't be a NS string literal, it just has to be like a car string. So let's call it Gameboy. Alright. Now we don't have to do this step, but it's always a good idea too, because we don't want to draw any like artifacts or anything. So we're just going to clear the renderer and just pass in a reference to the renderer. All right. So now, the way the renderer works is when we're just drawing pixels, it's going to just draw a single pixel, basically, a single color pixel. So we want to first set the background color, and then we're going to actually draw some pixels. So to set the background color, we'll use the Game Boy color palette. So we're going to use SDL set renderer draw color, and pass in reference to the renderer, and we're going to give it the hex colors for the background of a Game Boy screen, which is that weird pea green. I've got it here somewhere. Okay, here we go. So this is the background screen color, and then these are the 4 different pixel colors. So there's 100%, 75, 50, 25, and off, essentially. And that's how you figure out what colors are supposed to display. So we're going to use the background screen color, and the hex for that is OXCA, OXDC, whoops, OXDC, OX9F, and alpha. Now, we just call render clear again, and what that's going to do is it's going to not like clear the render, it just kind of paints the render, paints whatever is visible with the color that we've set to clear it to. So it's like clearing it to that color, I guess. You could set that to any color and make it the background black or blue or green or whatever. Now, we have to then set a pixel color, so we'll do set renderer draw color again, and we'll use one of those colors. So it's OXOF, OX3A, OXOF, and OXFF. All right, so now, if we do render clear again, it's going to paint it all that color, and we're not actually going to see that it's using 2 colors. So instead, we need to use a method called SDL render draw point. Draw point. All right, so we pass it a renderer, and we pass it a point. So we could do 1 and 1, and that will draw a pixel in the top left corner. But that's going to be quite hard to see. So what we'll do instead is we'll just have it draw a diagonal screen, diagonal line, because it's quite easy to do. 16. Then we'll just pass in I as the X and Y coordinate for that. So we'll copy that, paste it there, replace these with I. So that should draw a diagonal line, and then we'll present the renderer. Render present. Alright, render present actually draws the window to the screen. And what's interesting about this is it draws it as a separate window. So we're not bound to the window that we created, or rather that macOS creates for us. It actually creates a separate window, which is on the other screen. So I'll drag it down. So there we go. So that's our little test render there, which is cool. So we can see that SDL is working, and we can see that we can, if we had enough time or patience, we could go and paint something by changing each of the pixels one at a time. Cool. All right, so that's good. So we've got SDL set up. So now we can start looking at how we're going to actually create this Game Boy emulator. Now I realized that I should probably share that document now because there is a lot of following along. So just give me a moment. Let me get a link for it and I'll paste it in the chat. So this is the one that I was using. So we'll go copy link, paste in chat. There we go. CodeSlinger is a great website of this programmer who wrote all these like emulator tutorials as well. So if you do want to learn more about other emulators, it's really, really good. The tutorial that we're going through now kind of like leans on it a bit, because why bother reinventing that stuff? But we've made some changes to be a little bit more modern. Like, for example, he uses OpenGL, we're using SDL. We're making it really Mac specific, so we're going to use a lot of really interesting Mac things like drag and drop and stuff to actually get the ROMs in there. But a lot of it is based on this, which was made more than 10 years ago. There you go. All right, so I went and printed this using like one of those book printing services years ago. So I've got like a physical copy of it. It's a couple, how many pages is it? 140 some pages. So you don't have to print it, but I'm just going to be flicking through this book as we go along. So to emulate a Game Boy, we should probably talk about what that means. Basically, we want to make our computer do something that it shouldn't, right? We want to make our computer behave like a different computer, like a Game Boy. So the way we could do that is we could take every single game that's ever been made and we could port it to a modern operating system. And that would probably work, but it would take a real long time because we'd have to go through every single game. We'd have to make sure that it works right on the different systems, and it's not too fast and it's not too slow and it looks great. And every time a company makes a new game, we'd have to do the exact same thing. And if some company for whatever reason decided that they wanted to make a brand new game in 2019, we'd have to then go and port it again, and you'd never really win. So porting it's kind of out of the option. So what we want to do instead is we want to just be able to run it. We just want to be able to make the game think that it's running on a Game Boy, and just kind of reproduce all the parts that make up the Game Boy. Now, emulation has been around for a while, actually. There was this old thing. I'm just going to see if I can bring it up. It was called the... what was it called? VIC 80? No, not VIC 80. So there's this old concept of emulation, a VIP machine. All right, cool. So back in like 1970-something, 1976 or whatever, I don't know, there was this computer book, which the name escapes me. So this isn't a Byte magazine. There we go. This is going to be a really bad anecdote, but it's going to be an alright anecdote now. I'm bringing it back. Byte magazine, 1978. This guy wrote a brief for a theoretical language that could make it possible to run any program on any system. Because back in the early days of microcomputing, there were a lot of different competing systems, and it was really hard to know which one to get, because you wanted to be able to run programs that you wanted to be able to run, and because there were so many different ones and so many different implementations of processors and stuff, it just became really, really hard. Like, you'd buy a machine like a BBC or a Micro B or whatever, and you'd only be able to use like a small subset of programs, and it would take forever for companies to port them, and there was just a lot of fragmentation. So this guy decided, hey, what would be cool is if instead of worrying about porting your program to lots of different machines, why don't we just make our machines think that it's the same processor? And so he wrote this brief for a theoretical processor called a Chip 8. And it was very, very simple. It only had a couple of instructions, and if you go to the Wikipedia page for it, all the instructions are listed there in the Wikipedia page as like a subheading, which is pretty crazy. So I'll paste that in there. But what that allowed people to do is just write an implementation of the Chip 8 machine on their machine, or not download, or like, borrow one from a friend or get it from a magazine or whatever. And then they could run whatever apps they wanted, which is really cool for the time. So emulation's been around for a while. The idea of emulation's been around for a while, but the downside to emulation is a Game Boy, for example, is really specifically doing one thing, which is just playing Game Boy games. And the developers wrote the games pushing the limits because they wanted to, sell copies of their games. So they would push the limits of what the Game Boy could do, which means that any slowdown to that makes it a really bad experience, a really horrible experience. And emulation didn't really take off until maybe like late 90s, early 2000s, because computers just weren't really that fast. And so to emulate a Game Boy, because you're having to do everything the Game Boy used to do and more, and you don't have dedicated hardware to do it, you would end up needing a machine that was several dozen times more powerful than the Game Boy. The Game Boy wasn't very powerful. It was, I think, 4 megahertz, 4.19 megahertz. But, you know, the computer I had when I was a kid was 100 megahertz. So it's not really that much powerful. Like, it's a couple of dozen times more powerful, but not really when you think about it. If it's having to do everything the Game Boy does and pretend to be the display and accept keyboard inputs and run Windows in the background. So it wasn't really until late 90s, early 2000s that it really took off, with an emulator called, I think, No Cache or something, who knows. But I remember playing Pokemon with my brother with a Game Boy emulator like years and years and years ago, and it was terrible, but it was pretty cool. But now, because computers are so much more powerful, we can emulate whatever we want. You know, there are emulators for whole computers, virtual machines. Half the internet runs on emulated computers with like AWS and Google Cloud and Azure and stuff. So emulation's like pretty big, and a lot of processors now are releasing with mechanisms inside the processor to allow it to be easier to run emulated processors, which is kind of cool when you think about it. But they don't really support Game Boy, so we would have to build it ourselves, and it's all right. The computers that we're running now are powerful enough that it's okay. We can actually do it. So emulation breaks down into a really simple idea, which is the fetch, decode, execute loop. So what we want to do is we want to run through the instructions of the game. We want to fetch the instruction, we want to decode that instruction, and then we want to execute that instruction. And so what I'll show you, let me just launch terminal real quick. I broke my cardinal rule of not using Spotlight to find terminal, which is always great. So give me a second here. So we're going to use a test ROM because obviously there's a lot of copyright things that exist with ROMs, so we want to make sure that we're not using ROMs that we don't have the rights to use. So we're going to use a test ROM called CPU instructions. If you get into Game Boy emulation, you'll find a pretty big scene for Game Boy emulation and Game Boy development. And so this ROM here is more for just testing to see if the instructions that you've implemented actually work. The way it works is you run it and then you check a memory location after you run it, and it'll write to that memory location its state, if it was successful or not. Nothing displays to the screen. It's just to see if the instructions were successful. But what I want to show you, what is it called? CPU instructions, is what that ROM looks like. So here's terminal. Don't hate me because I don't use iTerm. I can't be bothered. I really like the normal terminal. And this is a hex dump of that ROM. So we can see the instruction counter on the, like the, what would you call it? Like the number or the line number? I don't know what you'd call it. But whatever it is, it's on the left. And these are in hex, which is why we've got weird numbers like 60 when there's obviously less than 60. And numbers like 2EF or 2EO and stuff, it's in hex. But the first instruction is 3C, second instruction is 39, 00, 00, 00, 00, and so on and so on and so on. So what we can actually do, it's tedious, but we can go through the book and we can find what these instructions are. So let's look for 3C. So we go to this is thrilling. It's actually going to take a real long time to find 3C, but let's pretend that it says 06. So 06 is the instruction LDBN, and what that means is we're going to put value NN into N. NN is it references like a register, and n is the immediate value after the instruction. So if this instruction was actually 06, then the next 8-bit number after that would be the immediate value. So the load instruction, this is interesting because there's multiple different registers, and so we need to have multiple different ways of figuring out what register we're going to load into, because there's how many other there's like 10 registers. So there's a different opcode, a different hex number for each of those locations. So the load instruction is actually like 8 instructions, but a different opcode represents those instructions, and that changes what the register that we're loading it into is. And then the immediate value after that is what we're loading into it. So let me give you an example. Let's say the instruction was 06 12. Yes. That would mean that we would load into register B the number 12. If it was OE12, then we'd look up the instruction, and we'd see that it's actually loading into register C the number 12, and so on and so on and so on. And so there's multiple different commands that we have, but the core commands that we use are like load and read and write and all that stuff. It's just a lot of doing that. So that's the fetch, decode, execute loop. We take an instruction, we decode the instruction, we execute the instruction. Very, very simple. And we're doing that multiple times a second. We're doing that at a speed of 4.19 megahertz, which is a lot. So, but our machine is much more powerful than that. The machine I'm running on now is a 1.8 gigahertz machine, so it's like several thousand times more powerful. So we need to make sure that we're not doing the instructions too quickly, otherwise it'll think like it's running in fast forward mode, which is interesting, right? Because there's a way then that we can change our emulator to behave like it's running in fast forward, or even rewind by changing the amount of instructions that we do every second. So to handle 4.19 megahertz, we'd have to limit the instructions to I'm going to show myself now. I think it's 4,190. I'm going to say it's probably way more than that, but we'd have to limit the amount of instructions we do. It's probably way more. Let me double check. Megahertz to hertz converter. Yeah, it's way more than that. 4.19 megahertz to hertz. Yeah, so it's actually 4,190,000. So it's way more than what I said. Because megahertz is a million. Oh, there we go. So we have to limit the amount of instructions we're doing to 4,190,000. But what's interesting though is every instruction doesn't take one cycle, because the speed of the processor isn't how many things it can do a second, it's how many cycles it can do. And each of these instructions takes multiple different, has different amounts of cycles that they take. So if we go back to that load instruction, what we'll see is that there's in the table, there's a number that says cycles, and that's the amount of cycles that it takes to do a load. So we're actually keeping track of that cycle count and making sure that we're not exceeding 4.19 million cycles per second. Once we reach that number, we just stop doing anything for that second and then continue the next second. That's the way that we can speed limit it to make sure that it's not running too fast or too slow. But if we change the amount of instructions that we're allowing to occur every second, then we can make it appear like it's running faster or make it appear like it's running slower. So if we say doubled it, we're essentially doubling the speed of the processor, which means it can do twice as many things per second, and so on. If we half the amount of instructions we allow it to do, then we're halving the speed of the processor, and it should run half as slow. So that's cycles. So let's let's do a very simple. Well, actually, there's a lot of pre-work we need to do before we can actually get to a point where we're executing instructions, though. So what I like to do is I like to just create a prefix header because we can typecast different values to make them make more sense to us. So let's make a prefix header. Now I remember prefix headers are actually really hard to make for some reason. Yeah, prefix headers, for whatever reason, they're really hard to make now. You have to do a lot of extra stuff. It used to just be file, new, prefix, but now it's a bit weird. So let's run through it together. So we go file, new, file. And then there should be some templates down here. We want PCH file. And then we want to just call it whatever our target name is. Actually, we just call it prefix header because it'll automatically do it. So we just go create. And then here's our prefix header. Then we need to tell Xcode to look for that prefix header. So we go to build settings, change this to all, and then there should be a prefix header field. Prefix header. Prefix header here. And then we're just going, so I'll see root. Prefix header.pch. And we use the correct symbol. There we go. So that expands it out. Prefix header. Very good. So now anything we put in here is accessible anywhere in the program. We don't want to go too crazy though, because it can make each of the header files quite massive. So we want to make sure that we're not like importing stuff in here if we really don't need it. Anything we import in here gets added to every single H file and can make the program huge. What we want to do though is we want to define a couple of things real quick. Let's just get rid of this comment. So the first thing we want to define is type def unsigned car byte, type def car signed byte, type def unsigned short word, and type def signed short signed word. All right, so the reason why we wanted to use these is it's very, very convenient. A byte is going to be 2 hex numbers, which is typically what we use mostly, and a word is going to be 4 hex numbers. I think that's right. I hope it's right. Let me double check. Because I think a byte is 8 bits. Yeah, byte's 8 bits, and a word is 16 bits. Perfect. So that is exactly what I said. I'm excellent. Byte and word. But we'll use these a lot. The signed bytes and signed words, we won't use that much. That's typically if we don't want the number to go into negatives, that kind of stuff. We'll use it a little bit. There's a couple of other things that we need to do as well. So let's talk briefly about registers. So the Game Boy, well, all CPUs actually, I won't say the Game Boy, all CPUs have instructions, right? They have wires connecting the parts of the CPU that do certain things together. So when you're adding numbers, your processor is using something called an accumulator. When you're dividing numbers, it's using something called a whatever it's called. But there are physical parts of the processor that are really, really good at doing that task. And it's set. So a processor just sets that. It's a bunch of switches aligned in a certain way that just does something, like an OR switch, an AND switch. If you've done any programming or any computer science in the past, you'll recognize those terms. But you can't change them. You can't change them on the fly. You can't make your processor do more adding than it is possible to do. If you had something like a FPGA, a field programmable gate array, you can adjust the switch layouts to make the processor do something else. And in the heyday of Bitcoin mining, people used FPGAs to make a processor be really, really good at doing whatever task Bitcoin needs. And then you would figure that out. You would then save it. You then make an ASICs, which is like a custom chip, and you're good to go. There's ASICs now in your iPhone. The Secure Enclave is an example of an ASIC. It's like a coprocessor that does one thing exceptionally well and nothing else at all. So Secure Enclave is an example of a ASIC. But all processors have the instruction set and they can do whatever they can do. But they also have some bits that you can store stuff in, so you can modify the contents of them, and they're called registers. And the reason why you'd want to use a register is if you want incredibly fast read and write access to just a number, like something. If you think about the amount of time it takes to read or write from a hard drive, it's trillions of times longer. I don't think it's trillions of times. It's several magnitudes longer to access from the hard drive than it is to access from the CPU, because it's right there. It's a very short distance to travel, and we are bound by the laws of physics, so we can't have electricity travel faster than it can, and so having the wire be exceptionally short and access something that's on the chip is always going to be faster. So all processors have a certain amount of registers. I don't know how many the processor I'm using right now is. Let's have a look. So I have an x86 register count. Alright, so the x86 architecture has 8 general purpose registers, 6 segment registers, 1 flag register, and an instruction pointer. 64 has additional. So we're using a 64-bit x86. Let's see. Yeah, there's a couple more. But very, very small number, because you don't really ever want to be accessing the registers when you're doing stuff on a guest operating system. It's not something you want to do. It's incredibly dangerous. So I don't believe there's actually any way for someone writing an OS 10 or iOS or Android or Windows app that runs on Windows or runs on macOS or runs on iOS that you can actually access the register. I don't think there's a way to do it. I think the operating system will stop you from doing that, which is good. You want that. You don't want to write to registers. It's dangerous. But when you're making an app for a console, and it's not really applicable now because PlayStation and Xbox and Switch are all running operating systems that are launching apps. But when you have a cartridge and you're just reading off the cartridge, there's nothing else that needs to access the registers, and so you may as well access them. And you had to make the app be fast, be quick enough that you'd actually want to play it. So the Game Boy has a bunch of registers. The count of which is, where is this? It's in here somewhere. Registers. It is all the way in processor. Memory map, I/O, cartridge types. This is thrilling viewing, obviously. Timer, interrupts, special registers, I/O registers. Cool. All right. There are 1, 2, 3, 4, 5, 6, 7, 8. Is that right? Yeah, 8 registers, I believe. Pretty sure. But the registers are weird. So each register can only hold an 8-bit number, but sometimes you'd need to hold a 16-bit number. So the way the registers work is that they're paired. Each register has a low and a high, and you can combine them together. So the pairings are very strange. Where are you? I really need to find this thing. Pairings pairings are very strange because it's not like AB, it's like AF or something. Like it's really, really strange. Well, we'll get back to it. But anyways, which is probably here. Okay, cool. So the pairings are AF, BC, DE, and HL. So it doesn't make a lot of sense. But we need to be able to access the high and low value of those whenever we want, plus also like access them at the same time. So one way we could do it is we could just create 8 properties or 8 IVARs and just use that. But that's kind of lame. So what we'll instead do is use a struct to handle that for us. So we're just going to create not a struct, a union. So we'll go to our prefix header, which we're already in, and we'll go union, register, word, register, struct, and then we have a low value and a high value. All right, so that's going to handle our registers. So now what we need is we need a couple of other things. To keep it like to the absolute bare minimum, what we could do is just kind of get those registers set, create some memory, so some cart memory, some ROM memory, and create like the program counter and all that stuff too. So let's do that together. Now we could just do it in the view controller, but since we can launch the Game Boy window from anywhere, we don't need to have references to the actual app delegate or window or anything. We'll go ahead and make a new class to be our Game Boy core. So it should just be a Coco class, subclass of NS object, and we'll just call it Game Boy core. Now, we could make it a singleton, but I don't think that's super necessary because it might just get a bit messy. So we'll instead just have a whole bunch of instance methods, not class methods. So the first one we'll do is we'll just basically copy and paste our display test window method to make sure that works. We'll need to import STL here, but we don't have to import it anymore from our view controller, so we can get rid of that call. And what we'll do is we'll I think that's the right syntax. I hope that's the right syntax. Okay, it's probably not the right syntax. I think that's it. Alright, so in view to appear, we'll go self.gameboycore equals gameboycore new, and then self.gameboycore display test window. Good, failed. Why did it fail? What's the problem? Build input file cannot be found. Did I call it something else? Prefix header. It's definitely there. Something else we need to do, Fatima, do you remember? Prefix header is always such a hard time with them. Do we have to do it in the project as well as the target? Oh, it might be this. This is a project name. I think that's it. Yeah. I think that's it. No, it's not it. It's not it though because I didn't. It's not it. It's not it because it's not wrong. It's not it because I didn't do this right. Because it wasn't giving me code complete. Aha. There we go. Been using Swift too long. Forgot the semicolons. Build succeeded. Hey. Alright, cool. So it's still working. We're still getting our... Where is it? Still getting our thing here. I don't know why it goes up to the top every time, but we're still getting it, which is good. Alright. So when the Game Boy is turned on, a bunch of stuff happens. The first thing that happens, let's do turn on Game Boy. Turn on, this is called turn on, because it's implied what we're turning on. Oops. Alright. So I'm going to put this at the top. I'm going to be a good programmer for once in my life. Put it at the top, and then I'm going to put pragma marks here. Tests. I'm not going to do test-driven development for this though. I'm not going to be that good a programmer, but I'll use pragma marks at least. And then we'll call this one pragma lifecycle. Alright, so when we turn on the Game Boy, we have to do a couple of things. The first thing we need to do, pretty sure I need to do something different there. No, I don't. Awesome. The first thing we need to do is just set the certain parts of the memory, because the Game Boy wants to run a program that's stored on its ROM straight away, and what that program does is it looks in the cart that's inserted into the Game Boy. It looks for a specific location to see if there is a bunch of code there, and it just compares it. And that's how it did its copy protection. Really, really basic. What it's looking for on the cartridge is the Nintendo logo. So when the Game Boy starts, the Nintendo logo scrolls from the top to the bottom, and it plays a little ding. The little ding is on the Game Boy, but the scrolling logo is on the cartridge. So those things combined together means that the cartridge is legit and means that it will run. Which is why when you're a kid, if you're playing a Game Boy and the cartridge is a bit dirty, the logo would look a bit screwed up, or it would just be completely solid because it's not able to read that part of it. Taking out, giving it a quick blow, puts water on the connectors, makes it a little bit easier for the connector to make a connection and read from that location. But that was its copy protection, which is kind of cool. So it's gonna check that when the cartridge loads, or when the Game Boy turns on. The location it checks is on the cartridge. Is it on the cartridge? ROM bank, switchable ROM bank. Yes, it's on the cartridge. It's location 0104 to 0133. So we need to set our memory to have those locations, and we need to have whatever's in those locations. Thankfully, I've done all this in the past, so I'll just copy and paste it. Otherwise, we'll be here all day. But what we want is well, copy this. Let's create our actual cart though, our ROM memory. So we'll just do them as IVARs because it's a little bit easier. We don't want to have to create properties. Also, they're not objects; they're primitives, so it'd be a bit weird to use a property for it. So we're going to create two things. We're going to create a cart memory, and the cart memory is going to be this long, and then we're going to create ROM memory. And the ROM memory is going to be smaller. Now, the ROM memory is, this is actually inside the Game Boy. And cart memory, you guessed it, is on the cartridge. Now you might be saying, Pat, those two numbers are different. How can that be? How can the internal memory of the Game Boy be smaller than the cartridge? That's a good question. The reason why is because the games were never really intended to be that big. No, that's not true. So the way the Game Boy works is it has a certain amount of memory, but it's very limited. And it really didn't know how big games would get. Like, I don't think when they created the Game Boy in whatever year they created, 1989 or something, playing Tetris and all those really simple games, I don't think they really expected like Pokemon with, you know, hundreds of different Pokemon with different sound effects and different attacks and story and all that stuff. They didn't expect that. So what they did was they were like, okay, cool. We don't know how big games are going to get, and we'll never know. So we're just going to allow games to swap out memory on the hardware itself every time it needs it. So what we have there is a whole bunch of different cartridges that have different memory types, and those memory types are swappable. So the game itself is responsible for making sure that it swaps the memory at the right time, and the Game Boy is just going to keep going, thinking that it's always reading off static memory, but actually it's allowing the part of static memory that it's reading from to be swappable. The best way to think about it is if you ever played music on a tape and you have to flip the tape over, or if you ever played music on a record and you have to flip the record over, or if you ever watched Titanic on video and you have to put in like tape 2 to see what happens at the end, because it's not a well-known story. That's kind of the same thing. The Game Boy is doing it for you though, and there are infinite tapes, or there are infinite sides to the record or whatever. But the Game Boy is allowing you to do that, and the game itself is responsible for doing that when it's supposed to. So we have a whole bunch of different things that we need to check on the cartridge to see what kind of memory it is, to see how we should swap it. For now though, let's just leave it. Let's just move on, because we'll get back to that soon. Let's just get our Game Boy's memory set correctly. So this is the memory. So we also need our registers, and our registers are those. We're going to use a union register, and then we're just going to call them the pairings, right? So register AF, register BC. So these are the different pairings we have. DE and HR. So there are 8 registers that are pairings, and so the way we would access them is like register AF.high or .low or .reg. That's how we access them. Very good. So we need a couple of other things. The Game Boy has other registers as well. It has a program counter, and the program counter is used to know where the Game Boy is up to with its execution, because it's reading through the game kind of sequentially, like the hex. I found the register, by the way. It's on page 62 of that book. It's reading through the hex of the program from the beginning, but what happens if there's like an if statement? It can't put the result that you're going to choose, because it doesn't know at compile time. So the program counter can kind of jump around and branch off to different things and stuff. And so right now, if you write an if statement, you're making the processor jump to 2 different locations in memory based on where your if statement takes them. So that's why we have a program counter. We also have a stack pointer, which is just a way to keep track of just a bunch of variables on top of a stack. Really, the stack pointer actually keeps track of the location of the top of the stack, and there's a certain certain allotment of memory in the ROM memory that is the stack, and it works like a stack. So first in, last out. No, that's not right. First in, last out. Right? That's a stack. Yeah, cool. Like a stack of paper, and then so we have to account for those 2. And then there's one more register we need to account for, which is the flag register. The flag register happens whenever like an operation occurs, like an add or a divide or whatever. Because it's an 8-bit processor, you can't count higher than 8 bits. So 8 bits is 255. And so what happens if the number is actually greater than that? Well, there's no way of knowing. So what it instead does is sets the value to the rollover value, and it just tells it just sets a flag, the flag register, to tell the program that it has carried, or it has gone below 0 or gone above 255, that kind of stuff. So that's the flag register. So we need to keep track of that as well. So the program counter is a 16-bit register, so we use Word for that. The stack pointer is one of those low-high registers, so it's going to be a union. And the carry flag is just a byte. Not carry flag, flag register. It's just a byte. So we can make a way that's easy for us to understand what's happening with the flag. Where are we? So we'll do that in we'll do it now. So there's only really 4 things that we care about with the flag register. Let's do it in our prefix setup. So we only care about the highest 4 numbers, the highest 4 values of that. So I'm going to write it out for you. So if you think about an 8-bit number, you've got 8 values, right? You've got 0, 0, 0, 0, 0, 0, 0, 0, 0. And you know, if you change this to 1, it's 1. If you change this to that, it's, oops, 1, 2, 3, 4, 5, 6, 7. All right. Did I screw up somehow? Yeah, so if you get like that, it's 2, and that's 3, and that's 4, and so on and so on and so on. We all know that. But what we care about with the flag register is the highest values. We care about this value, we care about this value, we care about this value, we care about this value. We don't really care about these values. Now, we can just have the register kind of increment by saying, oh, okay, B number 255 or 253, and that'll flip the 7th bit and 0 out all the other bits. But we might want to set 2 of those flags at once. We might want to set the Z flag and the N flag. So we would instead do bitwise operations to do that. So for us to set the last flag, we need to have a mechanism to do that. So we're just going to create quick little macros for us to do that. First thing we're going to do though is define what those flags are. So define flag Z is 7. Define flag N is 6. Define flag H is 5, and define flag C is 4. And then 3210 we don't use. Now if we look at the book on page 62, we can see that the Z flag is the 0 flag. So this bit is set when the result of a math operation is 0 or 2 values match when using the CP instruction. The N flag is a subtract flag. This bit is set if subtraction was performed in the last math instruction. The H flag is the half carry flag. This bit is set if the carry occurred from the lower nibble of the last math operation. And the C flag is the carry flag. This bit is set if the carry occurred from the last math operation, or if register A is a smaller value when executing the CP instruction. Cool. We'll get to those in more detail when we start actually implementing each of the instructions, because a lot of the time we'll have to manually set that. Well, not a lot of time, all the time we'll have to manually set it. So we'll go through that together. But what we're going to do is we're just going to create 3 very quick macros for us to test to see if a bit is is set, to set a bit, and to reset a bit. So let's go through that together. Test bit, and we're going to pass in a var and a pos, and then var and 1 doot that way. Pause. Cool. So we're going to pass in a number that we want to test to see if a bit is set, and we want to then pass the position of that flag that we're testing. So if we had a variable byte, whatever, hello equals OXFF, we know OXFF is 255, so which means every flag is going to be set. So then we could call if test bit, and let's just say 7, so flag Z, and that's not right, sorry, it would be hello, then flag Z, and then we could have it do something, because that would return true or false. So that's how we test the bits. Very simple. Alrighty, I need that's right about that. So now we want to be able to set a bit. Define set bit. Var and pause again, and this time. What's defined? Oh, I spelled it wrong. Bim. There we go. Thank you. I reckon that would have made me crazy. I would have been like looking through everything, trying to figure it out, looking through like the project settings, and it's just spelling. Womp womp. So now we use this command. Oops, not that one. This one. And then resetting the bit, which just makes it 0 basically. Pause. And %1. Well, it doesn't actually make it 0. So I believe it flips it. So if it's 0, it makes it 1. If it's 1, it makes it 0. So it's not really setting it to 0. Otherwise, we could just set it to 0. But I believe this one flips it. So anyways, there are 3 helpers to test, set, and reset bits. Perfect. Let's go back to our Game Boy Core, and let's see what else we need. Okay. So we're not going to worry too much about the bank just yet, but we'll need to worry about that soon. That's pretty much enough that we can use to get started setting the memory up for this. So in our turn on instruction, we need to do a couple of things first. The first thing we want to do is we want to zero out the registers. We want to make sure that any data that was in the registers is gone. There shouldn't be anything in the registers because we're creating primitives, so all primitives should initialize at 0. But since we're not actually initializing them, we just have them as IVARs, it can get a bit messy. So, you know, best practice is we just zero them out. If you don't zero them out, then it can create unexpected things to happen. The Game Boy didn't zero them out, but again, it was like a more tightly controlled, like you're not really pulling a game out and putting a new game in. You're always turning the game on, and by turning it on, it's setting those registers to 0 anyways. But we're allowing people to change the game on the fly. So to do that, we need to kind of simulate what it's like when the Game Boy gets switched off, and part of that is zeroing out the registers. So very tedious, but we just need to go through the low and high value of each of those registers and set it to OXFF. Is that right? No, that sets it to 1. So we want to set it to 0. So OXOO. Register AF.high equals that, and so on and so on and so on. 5, 6, 7, 8, and then we'll just do this low, 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 and then what's the next one? B. It's a BC. Yeah, BC, BC. What's the next one? TE. TE. H. Perfect. HL. Oops, HL. All right, very good. So now we need to zero out the program counter, the stack pointer, and the flag register. Now these have different values that we set them to. We set the flag register to 1. We set the program counter to OX100 because that's where the program starts executing from. And we set the stack pointer to OXFFFE. So that is our zeroed out things. Let's be good developers and make that its own method. Alrighty, so that's a good first step. So now we need to initialize the memory. So when we're initializing the memory, let's call it initialize memory, not initialize raw memory. Yes, let's call it that. And let's make another one. Initialize registers. And you know what? Let's be good here. Let's actually zero these out, because we can set them here. Perfect. So after we zero out the registers, we're going to initialize the registers, and then we're going to initialize memory. Raw memory. Yeah, let's call it raw memory. Let's go back to calling it raw memory, just to be confusing. All right, good. That's what I wanted. So when we're initializing registers, we set our registers to a certain value always when we start up. As I talked about before, the program counter is always 100. The stack pointer is always FFFE. And so the reason why it's always OXFFFE is if we look at the memory map, which is on page 8, actually it's going to be, they talk about the stack later on actually, sorry. On page 61, I think. 63. Yeah, so the stack pointer, the stack grows downward in RAM memory. The stack pointer should always be initialized at the highest location of RAM space that has been allocated for use by the stack. So whatever we've allocated for the stack, which is in the memory map, this has to be the highest accessible point of that, and then it goes down. The highest accessible point is OXFFFE, which is why we set it to that. Okay. Now we set the flag register to 1. Double check. Let me double check that that is correct though, because that doesn't sound correct. Because that would mean that the first instruction would have all the flags set, which is not true. So you know what? That's not correct. It's 0. And now we set each of the individual registers to something different. So register AF.reg, we set to OX01BO. Register BC.reg, we set to OX0013. Register DE.reg, we set to OX00D8, and HL we set to OX014D. Perfect. Okay, initialize raw memory. This one's way too long to type out, so I'm just going to copy and paste it. But this here is like the initial program that we want to set. Alright. So these values always have to be set in the ROM. Okay, so that's all our memory done. We have, what do we got? We've got all our registers, we've got a program counter, stack pointer, flag register. We've turned everything on, we've zeroed out our registers, initialized the registers, initialized ROM memory. So we're good to go. So if we run this, should work. We'll still get our test screen, but all the locations in memory that we care about are set the way we want them to be set, which is cool. So I realize now that we don't really have a way to access the memory. So if we wanted to store something in ROM memory, or if we wanted to copy something from the cartridge or whatever, we don't actually have a way of doing that, except by using like a literal, like ROM memory and a location, and then just grab it, like set it or read from it or whatever. But the Game Boy actually prohibits a lot of that behavior. We're only supposed to write to a certain portion of the Game Boy, and the challenge there is developers relied on things going wrong, like exceptions being called and stuff, to get the Game Boy to do stuff that was really unexpected. And so we need to be able to make those exceptions occur. And to have those exceptions occur, we need to be able to emulate the limitations of the hardware as well. In a perfect world, we could just write to whichever memory location we want, but we don't live in a perfect world. We live in the world we live in. And specifically, we have to follow the rules that the Game Boy has set. So if we look on page 8, we can see a memory map of what the memory looks like. And so the memory that we care about is from 0 to 4000, which is the 16 kilobyte ROM bank 0, and 4000 to 8000, which is the switchable ROM bank. So remember we talked about being able to flip the record? That's the part of the record that we can flip. And we can swap in and out as much as we want. Then from 8000 to A000, which is 8 kilobytes, is the video RAM. And then the video RAM also has a switchable RAM bank, which I believe was never used. Then from C000 to E000 is 8 kilobytes of internal RAM. From E to FE00 is the echo of that, the duplicated version of it. Then we've got like I/O ports and sprite attribution memory, and all that stuff exists in the last couple of bytes that that is between FE00 and FFFF. So if we keep going through the instruction, the programming guide here, it's going to tell us where we can and can't write from. Where are we? Page 61. Oh, it's page 10. I was like so close to it. It's page 10. It's reserved memory locations. Yeah, so on page 10 to 11 are the memory locations that we can't touch. But then also we don't want to write to an echo location. We want to make sure that if we're writing to a location that should be echoed, it is being echoed. We don't want to write to the internal RAM without permissions to do it, and that kind of thing. So what we really should do is create a couple of helper methods for when we are reading and writing from memory. So let's do that now. So we're going to call this pragma mark read and write helper methods. Okay, so the first one is read. Good thing I've prepared all these earlier. Read memory from address, and then we're going to pass in a address. The address is always words because the addressing is 16-bit. So now, there's a couple of things we can do. The easiest thing in the world to do is just return ROM memory address. That's the easiest thing in the world to do, and it would work. And most games would probably run fine with that, to be honest. But there are some that wouldn't. And the Game Boy games themselves also, it's not void, it's byte. The Game Boy games themselves expect us not to be able to write to certain locations, but also they expect that if we write to a specific location, that is duplicated in the echo. So we can't just do return ROM memory. All right. So what we want to do is the following. First one is if the address is greater than or equal to 4,000, oops, and address is less than or equal to OX7FFF. So this is safe memory. Safe memory. But we're not bothering to record the first 4,000 locations in our card memory. Do we have card memory? Yeah, we have card memory. Yeah, sorry, what am I talking about? If it's that location, it means that it's coming from the card, not coming from the ROM. I don't know what I was talking about there. Because it's just a contiguous kind of memory map. So if it is actually that, we want to take it from the cartridge. So we go word, new address equals address minus OX4000. Then we just go return, whoops, on a new line, cart memory, new address, plus, and now we haven't done banking, so I'm just going to create something that's going to represent what bank we're in, but we'll go through it in a moment. We haven't actually done anything with the banking just yet. So I'm just going to create something that's called current ROM bank equals 0. And we'll talk about that after we create these methods. But basically the ROM bank is going to be 0, 1, 2, 3, 4, and each of those ROM banks is 16 kilobytes. So what we know is that if it is ROM bank 0, then we don't have to do anything. If it's ROM bank 1 or 2 or 3, then we have to just shift the number that we're reading from to get the correct location. So it becomes current ROM bank, oops, new address plus current ROM bank times 4,000. Cool. So I hope that makes sense, but if it doesn't, let me try to explain it in a different way. If we are accessing the 4001, then we're in bank 0, then we're normalizing that address by getting rid of the 4,000. We're making it 4,000 less, so we're getting rid of the idea of like it being duplicates of 16 kilobytes. And then we're saying, okay, cool. If we're in ROM bank 0, we're then adding 0 times 4,000, which is going to be 0. So the new address is literally going to be 1. If it is ROM bank 1, though, it's not going to be 1. It's going to be 16 kilobytes ahead of that, and so we're just timesing it by timesing 4,000 by 1 because it's ROM bank 1 and 2 and 3 and so on. So that's why we do that little bit there. Current ROM bank times 4,000. All right. So now, else if address is greater than or equal to AOO and address is less than or equal to OXBFFF. Okay, so this is for a different kind of bank. If we're reading from this location, it's going to be in the RAM banks, which again we haven't really talked about. So let me create something that handles RAM banks. So RAM banks are a different kind of bank. Let's create a RAM banks here somewhere. Where are we? All right, let's create a RAM banks here. We can. I think we're just going to have to do banking, aren't we, Fatima? All right, so RAM banks are initialized to that size. So again, remember the internal RAM is, yeah, don't worry. Internal RAM is, why is this? Oh, because you can't initialize it there. There. All right, cool. I think we're just going to have to talk about banks. All right, let's power through and then we'll talk about banks. because banking is actually quite important. We're running into a lot of issues without having banking sorted. So this is going to be word new address equals address minus oxaoo, then return ROM banks new address plus current RAM bank. Cool. Current RAM bank times that, else return this. Okay. Let's talk about banks, because this is not going to make any sense without talking about banks. Right, RAM banks, yeah. Okay. So in the book, if we look at page, which page is it? Page 11. At memory location 0147, it defines what the cartridge type is. So there's a little guide there, but there's cartridge types like ROM only, which is like Tetris, I think, is a ROM only cart. And then there's ROM plus MBC1 plus MBC1 plus RAM plus MBC1 plus RAM plus battery, and so on and so on and so on. So if a cartridge had RAM on it, it basically was able to store stuff. So Pokemon was an example of a cartridge that had RAM on it, and it had a little battery inside it that was keeping the RAM powered, because RAM, as we know, is volatile. When power is removed from it, it resets. So we have to inspect that value and figure out what the cartridge type is, and then we need to do things that cartridge type is expecting, because that's what the Game Boy did. So let's see, a ROM only one, this is on page 13, a ROM only one is a 32 kilobyte, or kilobit, sorry, no kilobyte, 256 kilobit ROM, and occupies 000 to 7FFF. That's cool. MBC1 is stands for Memory Bank Controller 1, and it is you can get a 16 megabit ROM, 8 kilobyte RAM, or a 4 megabit ROM and 32 kilobyte RAM. So it's significantly bigger than the ROM only one. MBC1 defaults to 16 megabit ROM, 8 kilobit RAM mode on powering up. Writing a value into 600 to 7 FFF area will select the memory mode to use. S selects, yeah, cool. So it's just a number that's either 1 or 0. It's an 8-bit number, but it's just 1 or 0. And 0 is the 16 megabit 8 kilobyte mode, and 1 is the 4 megabit 32 kilobyte RAM mode. So we need to figure this out, we need to inspect that value to see what the kind of thing is, and so on and so on. So there's actually quite a lot of memory map things in here, of cartridge types. Now luckily I've already solved all this, so where possible I'll try to explain it, but for the most part I just want to get through it and get something that we can actually use, so I might just breeze through it. So the first thing we need to do is there's a couple of methods actually. Alright. So the first one is going to be just actually handling banking. Now we need to figure out what banking types we're going to support initially, because we'll go through and add more later, but each of them is quite a lot of effort. So the recommendation is just to support a few when you get started. So what we'll do is we'll support MBC1, MBC2, and ROM only, and we'll do that by using a enum. So we're going to have bank type MBC1, type MBC2, bank type unsupported, bank type ROM only, bank type. Cool. So the reason why I've ordered them this way is the default is going to be ROM only, but anything that's not 1 or 2 or ROM only should be unsupported, and eventually we can add more to it. We can like bank type, whatever, and we can just start adding it to it and removing the unsupported numbers. Okay. All right. So to start with, banking, we need a way to enable the bank. Void. Enable RAM bank if required for address, word address with data, byte data. Alrighty. I'm going to check if the bank type is bank type MBC2. If it is, we're going to bit address position 4. If that equals 1, we're going to do nothing. Then test data equals data. Track of if we're using RAM or not. We don't want to just do else because it might be garbage data. So we want to be really explicit. We need to set bank type as well. Keep track of that. All right. So that checks to see whether or not RAM bank is required. And so that's an important first step. Then we can actually handle the banking. Void handle banking with address and data. All right. So if the address is less than 2000, then we need to test the bank type. If bank type is equal to bank type 1 or is equal to bank type 2. As we add more bank types, it'd be probably easier to just say if it's not ROM only or not unsupported, but that's fine. Self enable RAM bank if required for address with data. That method we just created. Else if. So if the address is between 2000 and 3FFF. Then we check the bank type again, so I'm just going to copy this. And we want to change low ROM bank with data, so we need to create that method. Okay. change low ROM bank with data. Check if it's MBC2. And if it is, the current ROM bank is data and that's F. If the ROM bank is 0, make it 1, return. Get the lower 5 equals data 31, nope, and 31. Then we want to turn off the lower 5 for the ROM bank. We then want to OR that lower 5 with the lower 5 we just got from data. And then if it's 0, increment it. And that's it. And so in here, if it is between those two values, we go self, change low with data, data. Perfect. Now, else if address if it's between 4,000 and 5,000 sorry, 6,000, and if it's MPC1 only, then we change the high ROM bank, otherwise we just change the ROM bank. So we need to create 2 more helper methods here. Change high ROM bank with data. And we just go current ROM bank. Data. 64. Current ROM bank. Or data. And then if current ROM bank is 0, let's just increment that. So let's change high ROM bank with data. And then let's just change the RAM bank with data as well. Void change RAM bank with data. So we don't need to worry about low or high for this one. Just go current RAM bank. RAM. Current RAM bank equals data dut x3. Very good. There's one more, we'll just implement it while we're here, which is change ROM and RAM mode with data. Go byte new data equals data and 1 on banking, which we don't have. Just a boolean. Okay. So just keep track of if we're actually using ROM banking. ROM banking equals new data. There we go. So back to our handle banking. Alright, so if it is between those two values, 4,000 and 6,000, then we go, and it's MBC1, we go self, change high ROM, bank with data, else do the opposite, self, change RAM, bank with data. Else if so the last thing we're checking with the ROM banking stuff, saying can't see it because we haven't finished that if statement yet. Address is greater than equal to 6,000 and address is 8,000. If the bank type is bank type MPC1, self change ROM and RAM mode with data. Perfect. All right. So that is how we can handle banking. Very good. Now we've got our read memory thing. Now we need a write memory thing. So we're going to pass into this the address we want to write to and the data we want to write. Alrighty. So again, the easiest thing in the world to do here would just be ROM memory address equals data. Easiest thing in the world to do. But can't really do it that way because we can't write to certain locations. We need to make sure that we're doing the right thing. There's also a couple of things that we're going to breeze really fast over. Basically any of the timing stuff. There's a whole section on timing that we need to keep track of to see if it's, this is like clock frequency stuff, right? But every time a second passes, the Game Boy writes to a location that second has passed, and so we're constantly checking to see if it has actually passed or not. We're just going to skip that whole part for now. We're going to stub it out and then we'll get back to it just because it's ultra confusing. So this would be the easiest thing in the world, just to write straight to the ROM memory, but we can't do that because sometimes the addresses are going to be bigger than the actual memory. So we need to be careful where we're writing to. So what we've got to do is we've got to check first to see if we're writing to the divide register. Now the divide register is in this location. And so if the address is that, now I found with hex you have to put the hex number at the beginning of the if statement, not at the end. That must be an LLVM idiosyncrasy, I'm not sure, but for whatever reason you can't do address equals, you have to do the hex number equals address. I don't know why, but it's just what I found. So if we're reading, if we're trying to write to the divide register, we're just going to instead OXFF04. We're just going to instead set it to 0. I'm not going to actually write it. Cool. Now this is the memory stuff. Else if now there's a special location that is the memory location. It's called the TMC, and I'm just going to put it in the prefix header. This is all to do with timing. TMC, and TMC is location is OFFF07. There's a couple of other ones as well. I'll put them in here now, and we'll get to them when we get to them. TIMA, which is FF05, and oops, TMA is FF06. And then we'll also just keep our clock speed here, which is 4194304. Okay. So if the memory location that we're trying to write to is the TMC, we're just going to skip for now because it's very, very complicated. All right, now, else if the address is less than 8,000, we're going to handle banking with address, and the data. Very good. Else if address is between A000 and the address is between A00 and 00, which I believe is the internal RAM. It is the video RAM. So if we're writing to the video RAM, then if we've enabled RAM, new address is address minus AOO, and then similarly to what we did when we were reading it, it's RAM banks new address plus current RAM bank times 2000 equals data. Else, if we're in between EOOO and FEOO, which is going to be the internal RAM, then ROM memory address equals data, and then we're going to write the echo, self write memory with address, address minus 2000, so minus 8 kilobytes, and data. So that's just us writing to the echo location as well. Else if address is greater than or equal to OXFEAO and address is less than OXFEFF. So this location is restricted. So we're specifically calling out so we don't accidentally write to it, but we cannot write to it. It's going to be the registers and stuff, the internal registers. So we can't do that. And then finally, if all else fails, we can just write to the location. Perfect. So that's our read and write methods done. Perfect. Now, we're running out of time for this session, so let's just do some more initialization. We need to initialize a couple of the values we created for the banking stuff. Alright. So the first thing we need to do is we need to figure out what the bank type is. So let's create a, where should we put it? Let's put it in banking, even though it's an initialization method. Set bank type. Now, you'll remember that the bank type is stored in a certain location, 0147. We can see that on page 11 of that book, 0147. So we need to read the value of that. So we'll just do a simple switch. Cart memory, OX147. All right, now the cases are going to be, for the ones we care about, the different variations of MBC1 and MBC2. If we go to 11 again, it's 0, 1, 2, 3, 5, and 6. Those are the numbers that are variations of MBC1, MBC2, or ROM only. So we just do that. We go case 0, case 1, case 2, and so on and so on and so on. So case 0 is going to be ROM only. So we'll go bank type equals bank type ROM. Type ROM only, break. In case 1, case 2, case 3, case 5, case 6. So 1, 2, 3, 5, 6. Let's indent them. Now case 1 is MBC1, 2 is MBC1 again, 3 is MBC1 again, 5 is MBC2, and 6 is MBC2. Now default, if it's not any of these, it's just going to be unsupported. We don't need to break in a default. Alright. So when we're initializing our stuff, we're turning it on, but turning it on isn't really loading a ROM, it's just turning it on, right? So we need to tell it to load a ROM. And we'll just pass the ROM as NS data. And we'll pop that here. Alright, so we should probably keep track of the ROM. So let's create something called ROM data. Because it's a NS data, we can just use a property. Wherever possible, we'll try not to read and write from the NS data object because it does get a bit expensive. And then when we're doing this, we'll go self.rom data equals ROM. So then we're going to, load ROM, we're going to have to, I think we shouldn't let the user turn on the device. Let's instead have turn on be part of load ROM. So we'll make turn on a private method. Then we need to fill up the cartridge memory. So the way to do this is as follows. This is the most optimized way of doing it. I mean, you can just go one at a time through the NS ROM object itself, but this is a more optimized version. Using that buffer. Perfect. Okay. So that fills up our cart memory. So now we can set the bank type. And then we want to default the current ROM bank to be 1. Now we need to zero out the RAM bank data. The easiest way to do that is by using memset. Size of RAM banks. So that's going to zero out the RAM banks. We're then going to go current RAM bank equals 0, and that's that. We'll have our cartridge, we'll have all that stuff, and everything will be perfect. We won't actually know anything's happening, but everything will be perfect. So let me think here. Reading and writing, setting the bank type, handle banking, displaying the test window. So we're at a point now where we can actually start the fetch, decode, execute loop. But what we need before that though is we need the actual ROM. So let's just get that real quick. Alright. So will this be kind of cheeky where we have this display test window? We're just going to instead go load ROM. I'm going to pass that NSData object. Now it's in our bundle, so we'll just go NSData test ROM equals NSData data with contents of file. Do we need options? Nope. We need of type. Oh no, just need a file. And it's going to be ns bundle, main bundle, path for resource. The resource name is CPU instrs, and the type is GB. Cool. We can just pass that test ROM straight into here. Now we'll need to know when it's done. So when it's all done loading the ROM, then let's get it to display the test window. Let's make that a private method as well. Right, let's see. So we'll run that. Build succeeded. And we have a screen, which is good. So now we're ready to fetch, decode, and execute. So let's go to our load ROM. Oh, we're right there already. And what we need now is a method called update emulator. Let's see. I know we need a begin method, I think. Yeah, we need a begin method. Actually, what time is it? I think we'll have to leave the session there, but we'll continue where we left off. When we upload this to YouTube, we'll include a copy of the project at this point, so you can continue on or experiment with it or whatever. But thank you so much for watching. Be sure to check out our development blog, oneflare.io, and follow us and like us and subscribe and all that good stuff. And we'll catch you next time. Thank you so much. Bye bye.